Hey everybody, this is Mr. Beckstrom, and today I'm taking a look at one of the questions from the forums. And it says, show that the equation that the tangent of theta is equal to the square root of secant of theta squared minus 1 is not an identity. So the idea of this is that three of these are going to end up being true for this equation, but one of these is going to end up not being true for this equation. So we can go through and check each one of these and see for which one it's not true. But for this one, what I wanted to do was get a little bit of practice using our calculator. So I want to go ahead and get your calculator out for this. All right, and once you do, it's going to be a little bit tricky putting this stuff in, but we can definitely do it. So I want to first make sure, let's go ahead and put in radians for this. You can do it in radians or degrees, it doesn't really matter, but I'm going to go ahead and use radians. And then I'm going to go to y equals, and on one side of the equation, I'm just going to put in the tangent of theta, or tangent of x in this case. That side is going to be easy. Tangent of x, and on the other side for y2, that's where I'm going to put this. So it's going to be the square root of that. So we're going to do the second square root, and then it's going to be the secant squared of theta. And let's see how we're going to write that out. Remember that the secant squared of theta, what that really means is the secant of theta squared, and that's how we have to think about that function. That's really, when you put the squared in here, that's really shorthand for this function here, or this function there, squared. And then secant of theta is really 1 over cosine of theta, since we don't actually have a secant theta button, so that's really just 1 over cosine of theta quantity squared. So this is how we're going to write this in our calculator for secant squared of theta. So we really have to kind of do that in 2 steps. So I'm going to do in parentheses 1 divided by cosine of x, and then close parentheses squared, like that. Make sure you do that double parenthesis. You need one parenthesis for the x, and then the other parenthesis to close in that 1 over cosine, and that takes care of that secant squared of theta. And then you're going to have the minus 1, oops, go back 1, minus 1, like this. So that will be our other one. So now we have the tangent of theta for y1, and we have the square root of secant squared of theta minus 1 for the y2. And this can really be done for any of the identities that we're kind of checking. And so this is a really good skill to have, to be able to put these into our calculator, and we can check multiple values to see if we believe something is an identity or not. If we check a bunch of different values and they're the same for each one of those values, chances are it's an identity, and then we can go through the process of proving that it's an identity. If we can find a value that it's not the same at, then that one value where it's not the same, then that proves that it is not an identity. All we need to do is find one value where it's going to prove to be different from one side to the other, then that's all we need to show that it's not an identity. Let's see how it works in this case. So now let's go ahead and second quit to get out of here, and now I'm going to put these into my table. That's the quickest way to do it. So if you hit second window, that'll go to your table setup. Make sure your independent is on ask and your dependent is on auto. Mine will usually default to that, but you always want to check that, because you want to make sure it asks you your x value and it automatically does your y values, your y1 and your y2. And then if that's good, you're going to hit second graph, and I'm going to clear this data out here. So delete, delete, delete. And then I'm just going to start putting in these 4 values and see when I get y1 and a y2 that are different from each other. So let's try 3 pi over 4. So 3 second pi divided by 4. And, oh, right away, this value is -1 on the left and a +1 on the right. So let's see about these other ones. How about pi over 3? So second pi divided by 3. Those ones are the same. How about pi over 4? Second pi divided by 4. Those are the same. And how about pi? Second pi. And those are the same. So notice that so we might check all 3 of these first, B, C, and D first, and say, oh, this has to be an identity because it's the same if we put in all 3 of these values. But as soon as we check that for this one value here, we get a different value on both sides, then this single value shows that this is not an identity. That means all we have to do is show that there's this one value out there, any value, where they're not going to be the same on both sides. And then we'll be able to also see that graphically, because for this to be an identity, both of these have to be the exact same graph. So now I know that these are actually going to end up being different graphs. So let's take a look. And as you can see, they are different graphs. So one of them kind of goes down here and comes up here, and then the other one goes down there and comes up there. So you can kind of see this portion here is the same on both of them, but once we put in x values on this portion, they're going to be different. So when all 3 of these values are kind of on this right hand side here, where they're going to be the same, but once we kind of go on a left hand part of one of these, they're going to actually be different y values. Alright, I hope this helps. This is a really good tool to have in our toolbox when we're trying to verify identities, and looking at that graph, seeing if it's the same graph. If it is the same graph, then that's going to tell us that yes, more than likely these things are identities, and we should go through and try to prove that they are. In order to prove something's an identity, we just have to manipulate both sides of the equations using known techniques until we get them to match, and we'll look at some of those as well. All right, I hope everybody has a great rest of your week, and we'll see you soon. Thanks. Bye-bye.